So, yes, the thing is recorded. So, welcome everybody to our Soda Labs webinar series. It's a great pleasure to welcome Martin Huber today. Martin Huber and I go back quite a long time. We did our undergraduate studies in Innsbruck together and did some courses together. And share a passion for skiing and snowboarding. Martin Huber is from the University of Fribourg, and he does super interesting things broadly about machine learning. And today he will talk about causal mediation analysis with double machine learning. As usual, you're more than welcome to ask questions, brief questions in between the talk. And if it's somewhat longer questions, just pop them into the chat and Ashani and myself will basically moderate the questions. Other than that, as usual, we have about 1 hour. And Martin, the floor is yours.
Okay, thank you very much for this invitation. It's a great pleasure to be invited to this seminar. And I also do hope that the situation in Melbourne will ease soon. Let me just close here some stuff, okay. And go to full screen. Right. So here we are. So this paper is on causal mediation analysis with double machine learning. And this is joint work with Helmut, Farbmacher, Lukas, Laffers, Henrika, Langen, and Martin Spindler from various universities. And in a nutshell, actually, the project is about disentangling a total treatment effect into a direct component and an indirect component that operates through an intermediate variable. So we will see some examples in a minute. And in this specific paper, we look at the setup where we have a potentially large set of control variables to guarantee that the identifying assumptions for identifying the causal direct and indirect effects are satisfied. And we will use so-called double machine learning to control for these control variables in a data-driven way. That is to say, to find among the large set of control variables those covariates that are important to rule out confounding such that the effects can be consistently estimated. So I will give you a brief introduction to the topic. I will discuss the identifying assumptions. I will discuss our double machine learning framework then as well for estimation. If I have time, I will also briefly show some simulation. And then I also have a little empirical illustration, and then I will conclude. So what are actually causal mechanisms, or what are direct and indirect effects? What is the motivation for this? Well, in many economic problems, we are actually not only interested in the total effect of an intervention or a treatment, such as the average treatment effect, but also the causal mechanisms through which it operates. And if we have causal mechanisms, well, it means that the treatment effect operates through intermediate outcomes, or so-called mediators, that are on the causal path between the treatment and the outcome of interest. And just to give you some examples, in labor market economics, we could, for example, be interested in the employment effect of a training program. And it could be that we want to know exactly whether the training program, the first training program per se, actually has a direct effect itself, or whether the effect of some training program only materializes through further program participation, right? And then if it was only through further program participation, then this would be an indirect effect, right? Because very often, for example, you have something like a job application training first, and then it might be followed by, for example, a language course or a computer course. So you have a sequence of programs. And very often you want to know, well, the first program itself, the job application program, does that already have an effect net of the further participation in the computer course or not, for example. So here, this would be an example for disentangling the direct from the indirect effect. Or the second thing, think about the health effect of education, right? So education affects health, but then the question is, for example, does education affect health through employment? Because we know that employment is correlated with mental health, right? So education could increase health through increasing employment, and that would be then an indirect effect because employment would be the mediator. Or are there also other causal mechanisms? And then we could just subsume these other causal mechanisms within the direct effect, right? So for example, such other causal mechanisms could be peer effects, because if you attain more education, you meet different people than if you don't, for example. However, the problem with identifying such causal effects or causal mechanisms is that even if the treatment is randomized, we cannot easily actually disentangle direct and indirect effects, because a naive approach of just controlling for the mediator would in general introduce selection bias or endogeneity, because even though the treatment is randomized, the mediator itself is a post-treatment variable, right? It's so to say a bad control, and therefore if we just control for it, we introduce bias if there are unobservables that jointly affect the mediator and the outcome. So therefore, we need to control for the confounders of the mediator, those variables that jointly affect the mediator and the outcome. And if we don't have a randomized trial, then of course we also need to control for the confounders of the treatment. And the idea in this paper is to do this in a context where we have a large set of potential control variables and pick the important control variables in a data-driven way by machine. Just relatively briefly on the literature, mediation analysis goes back quite some to some studies like Cochrane in 57 or Judd and Kendi 81. And the seminal paper, however, that triggered a large literature is the one by Barron and Kendi 68. And what these papers usually have in common is that they use very simple linear models. So they use something very similar to two-stage least squares, where they have a linear model for the mediator and a linear model for the outcome. And very often these early papers do not consider confounding. So they actually ignore the endogeneity problem. More recently, there's a larger semi-non-parametric literature that also uses the potential outcome framework, and that explicitly thinks about assumptions that allow identification and tries to control for confounders, mainly assuming that all the confounders are observed. So it's mainly selection on observables. There are also some applications of this now in the econ literature. For example, for disentangling cognitive and non-cognitive mechanisms of early childhood interventions, or also in labor economics in the way I described it before. A paper particularly relevant for our study is actually the paper by Chetkin and Spitzer 2012. Because what they show is they give an identification result which relies on a so-called doubly robust function for identification. Doubly robust functions are functions where I have models for where I identify effects both by using a model for the outcome and a model for the propensity score and a model for the mediator. And by using all this information, you can actually show that evaluation of direct and indirect effects on such doubly robust scores is robust to small estimation errors, for example, in the conditional mean outcome or in the mediator function or in the treatment propensity score. And this is key in the context of double machine learning. And also here, double machine learning, so this has been actually described in a paper by Chernoshukov et al. Because if you use a machine learner to learn these functions, for example, the conditional mean, you will make estimation mistakes, because machine learners are in generally biased. So it's important to use a function which is robust to at least small biases in these functions. And so what the idea of this paper is that we combine these doubly robust or so-called efficient score functions with the double machine learning framework in this paper. So this is then the evaluation of direct and indirect causal effects under selection on observer's assumption with a high dimensional set of potential control variables, where we then combine this double machine learning framework with these efficient score functions. And one particular feature of this double machine learning framework is that you combine it with sample splitting. That is to say, you use different parts of the data for learning the models of the conditional mean outcome, of the treatment propensity score, and of the mediator model. And a different part of the data for estimating the treatment effect. And by doing this, you have no correlation in the estimation steps. So you have no correlation in the estimation of the first step estimators, for example, for the conditional mean outcome, and the second step estimator of the treatment effect. And this turns out to be key for having nice properties of the estimator, namely root n consistency and asymptotic normality of the treatment effect estimator. When using machine learning estimators for these first step parameters like the conditional outcome. And you can allow for a fairly slow convergence rate in these first step estimators, or let's say at least a slower than standard convergence rate in these first step estimators. So it suffices if you actually estimate each of these first step estimators for the outcome model, for the mediator model, and for the treatment model with a rate which is not slower than n to the power of -1/4, which is slower than root n. And that effectively means, well, you can make some mistakes in the estimation as long as the mistakes vanish with this rate at least. And then even though you have such a slower estimator, you still get root n consistency and asymptotic normality of the treatment effect estimator. And the other nice thing is that this first step estimator does not even contribute to the variance of your treatment effect estimator. So what that means is, if you have a large enough sample, then the variance of your treatment effect estimator is unaffected of the machine learner. And this is nice because the machine learner is here to pick the covariates, right? So that means even if you don't know which are the important covariates to pick, right? So that means you have another estimation step for picking the covariates. In spite of this additional estimation problem, you actually end up with the same variance in large samples for your treatment effect estimator as if you had known the covariates which you need to include a priori already. Right? In classical treatment effect estimation, we assume that we know all the covariates which are important to control for. And here we don't do this, and this additional step of estimation or of selecting the important confounders does not contribute to the overall variance under these assumptions. So let me briefly outline what direct and indirect effect identification is about, because maybe not everyone is familiar with causal mediation. So first of all, let me introduce some notation. We will actually denote by M of D the potential mediator under treatment 0 or 1. So we have a binary treatment which can be 1 or 0. And then using the potential outcome mediator, the M of 1 would be the mediator. So for example, the health state of some, or the employment state of some individual, if the individual was treated, if the individual, for example, received training, and M of 0 would be the employment state if the individual was not treated, for example. We also use the potential outcome notation for the outcome, but now, as you see here, the potential outcome is a function of both the treatment and the mediator. right? So here you can think about what would be the potential outcome, for example, if a person was treated and if a person found employment, for example. So this could be the potential health outcome for this individual had the individual found employment and had the individual being treated, for example. Now, to disentangle these effects, we need to first acknowledge that the treatment can actually have an effect on the outcome, either through the mediator or directly, right? So the total effect of the treatment is given either by the direct effect or by the effect of the treatment on the outcome operating through the mediator, right? This is sort of related to the instrumental variable context. However, in an instrumental variable context, you don't have a direct effect, right? So for example, in the instrumental variable context, D would be the instrument. The instrument would affect this variable M, and M itself, the second stage, would affect the outcome, and we would rule out a direct effect. But here in mediation, we allow for a direct effect as well. And here actually D is the treatment we are interested in and not the instrument. So to characterize the so-called natural indirect effect, what we want to do is we want to fix the treatment at a specific value D. And we want to know what the difference in mean potential outcomes is if we vary the mean potential outcomes as a function of the potential mediator state, right? So this here would be the potential health if employment was set to its value under treatment. And this would here be here the potential health if employment was set to its value under non-treatment. So, and then the difference in these two gives us the indirect health effect, because it is the effect of the treatment on health, but only that part of the effect of treatment on health that is actually operating through a change in the mediator. Because what you see here is that the treatment itself is fixed at D. D can be either 1 or 0, but we vary the mediator according to its state under treatment and non-treatment. And that gives us the indirect effect. Right? Because the difference in the mediator under treatment and non-treatment gives us the first stage. And then how does this first stage affect the health? That difference is given by the second stage. Exactly the other side of the coin, if you want to put it this way, is the direct effect. So in the for identifying the direct effect, which we denote by theta, what we do is we fix the potential mediator at some value, either under treatment or non-treatment, but it remains fixed. And we vary the treatment from 1 to 0 to see how the potential outcome changes if we fix the mediator but vary the treatment. Now, as the mediator is fixed, there can by definition not be an indirect effect. So if we observe then that something changes in the outcome, this must be the direct effect. A very important detail at this moment is that you see here that the indirect and the direct effects are both a function of D. And that means the direct effect can differ depending on whether we fix the mediator at its value under treatment or under non-treatment. So it could, for example, be that the direct effect of a training is particularly large when we fix the mediator under its value under treatment. So that means when there are more people who are employed. So it could be that if direct effect is particularly large for employed people, but not so large for unemployed people, right? So this makes clear, this notation makes clear that there might be interaction effects between the treatment and the mediator going on. And if we have such interaction effects, well, that means that the indirect and the direct effects actually depend on the D here. And then, not very surprisingly, both kind of effects add up to the total effect, so to the average treatment effect. However, and this is related to the thing I just said, you either need to attribute this interaction effect to the direct effect or the indirect effect, but not to the same effects at the same time, to both effects at the same time. So that means you can either show that the total effect consists of the direct effect under treatment, where you now see that we fix the potential mediator to its value under treatment, so the employment state under training, for example, plus the indirect effect under non-treatment, where you now see we fix the treatment to be 0, or the other way around, the total treatment effect can also be shown to correspond to the direct effect under non-treatment, where you see here it's m of 0, plus the indirect effect under treatment, where you see the treatment is 1 here, right? So this is important. The interaction effects, of course, cannot be accounted for twice. So therefore, there are different ways to define direct and indirect effects, depending on whether you look at the direct or indirect effects under treatment or non-treatment. Right? How do I do this decomposition? It's actually quite easy by just subtracting and adding these potential outcomes here. Then you get from this first line to the second line, and this then allows you to show what the direct and indirect effect is. And a very similar thing here in the third line. Okay, then there's also, which is something else, which is called the controlled direct effect. And let me just briefly discuss the difference here. In the so-called natural direct and indirect framework, you see here that we condition on a potential mediator. That is to say, it's the individual's decision what their mediator value is. Right? This is similar to compliers, defiers, always or never takers in instrumental variable setups, because there might be individuals that always get employed, no matter whether they are trained or not. So they are always takers. Or there might be people who never get employed, no matter whether they receive the training or not. So these are never takers. And here it's really the individual's decision, right? What this potential mediator looks like. We could also be interested in enforcing a mediator for everyone, right? So setting the employment state to 1 for everyone. And then this would be a prescribed direct effect. So, and therefore this is then called the controlled direct effect. In this talk, however, I will focus on these natural effects for identification. So let me just briefly have a look how I'm doing in terms of time. Okay, good. So now the identifying assumptions in this framework, which I use, can actually be characterized by this simple graph. So what you see here is, first you see the same graph as before, right? You see here the direct effect and the indirect effect running over the mediator. Now what we assume is that we can actually observe all the confounders that either jointly affect the treatment and the outcome, or the treatment and the mediator, or the mediator and the outcome. And we will assume that pre-treatment confounders are sufficient for controlling for any form of confounding. In this system, we could still allow for unobservables that either affect the treatment, either affect the mediator, or affect the outcome, but we cannot allow for unobservables that jointly affect 2 out of our 3 important variables here. Right? So this is a selection on observables assumption. However, now in the context of mediation analysis, if I want to formalize these assumptions, I can do so by a set of conditional independence assumptions. So the standard assumption used in treatment evaluation is this one, namely conditional on X. The treatment is independent of any post-treatment, so any potential post-treatment variables like the potential mediator and the potential outcome. Now here in the mediation context, I also need a second conditional independence assumption, namely that also the mediator is conditionally independent of the potential outcome after controlling for the treatment state and the variables X, right? So if we go back here, there are no unobserved confounders jointly affecting N and Y after controlling for X and D. And then finally, I need a common support assumption. So what you see here is this is the treatment propensity score, and the treatment propensity score given X and given N must be larger than 0 for any value of D, where D can be 1 or 0. So what that means is for any combination of the mediator and the covariates, I need to observe both treated and non-treated individuals in the population. So this is a little bit a stronger assumption than a classical assumption that we have in treatment evaluation. Namely, usually we have that the probability of the treatment given X must be larger than 0. But here it needs to be given M and X, as we are now doing mediation analysis. So we need a slightly or a somewhat stronger common support assumption. So now let me come to the formula of this score function, which will underlie our estimator. So this goes back to paper by Chetkin, Spitzer, 2012. And what they show is that you can identify the counterfactual outcome, so the average of the potential outcome under D, where the mediator is defined on the opposite treatment state by this formula. And this is actually the key thing you want to identify, right? Because this is something you cannot observe in reality, but what you need for mediation analysis. You want to know what the potential outcome is, for example, under treatment, if the mediator would be in the opposite state under non-treatment. And the identifying assumptions allow identifying this on average. And you see, it's just an ugly formula, which none of us needs to know by heart. But what you should see is that it has some components in there, namely the density of the mediator, the conditional density of the mediator. Then this thing here is the treatment propensity score given X. So this is described down here. And this mu here is the conditional outcome given the treatment, the mediator, and the covariates, right? So based on this function, you can identify the treatment effect. Now, this function has has one shortcoming, which is from an applied perspective, not so nice. Namely, you have here this mediator density in there, and also here. And conditional densities might be hard to estimate in practice, in particular if you have a mediator which is continuously distributed, or you also have multiple mediators. So our framework also allows for several mediators, and then the indirect effect is the effect going through any of these mediators. And then if you have several mediators, so that then these densities become cumbersome to estimate. So what we do in the paper, by a simple application of Bayes' law, we reformulate this expression of Chetkin and Spitzer and show that it can be reformulated in a way that you get rid of the density functions. And instead of this density function, you have now a treatment propensity score. So you have a second treatment propensity score, which is where you condition now on M and X. And the nice thing about this is that treatment propensity scores are easier to estimate than conditional densities, right? Because here you just have a binary variable. So in a parametric framework, you could just use a logit or a probit model. But here we will use actually a machine learner for all of that, right? So that avoids the estimation of this density. So therefore, this is the first contribution in our paper. And the second contribution is that we actually combine this with double machine learning. Now here you see further functions. This is actually here's a typo, but never mind. So this here would be the standard potential outcome in the standard treatment evaluation literature, but this has also been already derived. So this is in terms of doubly robust scores. So this would be the doubly robust score we get. But this has been derived in earlier papers already. So as I said, in our context, we assume that X is high dimensional. And what we need to estimate this, well, we need plug-in, what we need to estimate this function here, for example, well, we need plug-in estimates for this conditional mean, the propensity score, and if we use the Chetkin-Spitzer approach, also for the conditional density. So therefore, what we will do is we will actually use machine learners for estimating these parameters. So, and this is attractive if X is high dimensional and you don't know which are the important confounders to control for a priori. The disadvantage of using machine learning, however, is that it typically yields a biased estimate of these parameters because not so important confounders are actually dropped, right? If you use, for example, Lasso. So even confounders that actually do predict the outcome and the treatment, they are dropped by the machine learner if they are not so important, because the machine learner tries to find an optimal trade-off between the bias and the variance. And for this reason, you should have a treatment effect estimator, which is robust to small errors in estimating these functions. And therefore, the robustness property of these doubly robust score functions is key for a well-behaved treatment effect estimation, despite the bias which is introduced by dropping the not so important covariates from the outcome or treatment equation. So that means this is, by the way, called regularization bias. If you have a bias due to not including all the x variables that should be. So these doubly robust score functions safeguard against this. But then you have a second bias in this setup. And the second bias comes from the fact that if you use one sample to conduct both the estimation of these first step parameters and the estimation of the treatment effect, then these two estimation steps will be correlated because they are done in the same sample. And that means you can have overfitting bias. Overfitting bias means that you actually fit these models to the specificities of the sample. And that means that you could fit part of the error terms of these different equations, which you shouldn't do because that would then increase the variance. And in a different sample, you would not have a good estimate then anymore for this new sample. So therefore, in order to avoid this, you use so-called cross-fitting or sample splitting, where you use one part of the data to estimate these models and the second part of the data to estimate the treatment effect. Now, this, however, has the disadvantage that you lose a part of your data, right? Because then you would only use, for example, half of the data for estimating the treatment effect if you do so. So therefore, a thing you can do is swapping the roles of the data sets. So first you use one part of the data to estimate the plugin estimates here and the other part of the data to estimate the treatment effect. But then you swap the roles and do it exactly the opposite way. And then you can simply average over the treatment effects in the two subsamples that you have estimated. And this is called k-fold cross-fitting. And that avoids that you lose observations for estimating the treatment effect. And it can be shown that asymptotically, it does not change the variance of your estimator. Even though in small sample, it could entail a slightly larger variance, one has to say.
Martin, I think Klaus has a question.
Yeah, thanks for pointing this out because I unfortunately don't see here who's asking questions. Yeah. Please go ahead, Klaus. Hello?
Klaus, you're still mute.
Yeah, I unfortunately cannot hear it. Maybe Klaus could write it.
Yeah, does it work now, Klaus? Can you talk? Okay, maybe you can ask it later.
Okay. So
he's
then
restarting Zoom. Okay.
Yeah. So in this case, I will continue if there are not, if there are no more questions. Okay. So how does the estimation algorithm look like? And so the estimation algorithm looks the following way. You actually split your sample into various subsamples. So it could, for example, just be 2 subsamples. And then what you do in one of the subsamples is you estimate this conditional mean outcome and the propensity score and so on and so forth. And this would be the subsample called WKC. And then in the other part of the data, you then do the prediction of this robust function, which we have seen before. So you then do the prediction, you estimate this function here in the other part of the data. And then finally, you just swap the roles and do it again. And then you average actually over these two treatment effects, which you estimated in the subsamples. I will skip this. This is actually what I already mentioned before, but now just in concise mathematical terms. But you need some regularity conditions on these first step estimators to have then consistency of your treatment effect estimator. And the key assumption is this following one here, namely that you need to estimate the conditional mean or the mediator model or the treatment model with at least consistency of with a convergence rate of n to the power of minus 1/4. And it has been shown for several commonly used machine learners that this rate can be attained. For example, it has been shown for the Lasso Estimator, it has been shown for random forests, it has also been shown for deep learning like neural nets and for so-called boosting estimators. Then I have a simulation study as well, but in the interest of time, let me skip the simulation study because to make it very brief, the simulation study shows that the estimators appear to do what they should, namely as the sample size increases, the bias and the variance get smaller. And in the simulation design, we considered at least they show a root n behavior. The treatment effects show a root n behavior. And we actually looked at this for both the Chetkin Spitzer estimator, and we looked this for our refined estimator, where we don't need to estimate densities of the mediator. It turned out, for the example we had at least, our estimator showed a slightly better behavior, maybe related to the fact that you don't need to estimate these mediator densities. I just see that Sasha has a question now.
Yeah, hi. Just to make sure I understand, the Chernozyukov stuff on double robust selection, my understanding was that you independently try to find predictors for the treatment equation and then for the outcome, and then you pool the set of predictors. This is not what you do here, right? These two steps, the two separate prediction steps are kept separate, and the set of variables found is not pooled, right?
So the framework you are referring to is actually the so-called double selection framework. And this is slightly different to the double machine learning framework.
Okay.
So a double selection framework, you would indeed first by Lasso find the variables that affect the treatment, then find the variables that affect the outcome. And then ideally, again, in a separate part of the data, you would run, for example, an OLS regression of the treatment on the outcome, including all the variables that have been found in one of the two first steps. So that either affected the treatment or the outcome. So you would take the union of this. Now here, in the double machine learning framework, which is a different paper by Chernozyukov, here the idea is actually that you directly estimate the propensity score or the conditional mean outcome. So you don't collect the control variables and then run another outcome equation. What you do is you directly estimate the propensity score and the outcome, and then you plug these propensity scores and outcome estimates into this robust function, right? So it's a different way. Both double machine learning and double selection have the same goal, namely finding and controlling for the X variables that are important, but the approaches are technically somewhat different.
Okay.
Double selection approach has been shown to work for the lasso, right? Because the lasso actively selects variables. Whereas the double machine learning approach can also be used for any machine learner which does not actively select X variables. For example, in a random forest, right, you split the data according to values of X, right? And it also works for these kind of machine learners.
Thank you, Matt.
Yeah. Okay, so, but a very good question, yeah, because there are a lot of different approaches out there now, and it's not always easy to keep track in this fast-moving literature. So let me conclude.
Martin, if I may interrupt you, I think Victoria has a question as well.
Yeah.
Yes, thank you so much. Sorry for interrupting, but yeah, my question was just about, in this particular case, am I understanding correctly that you're interested in one particular mediator, and so the issue is you're just wanting to essentially sort of control away any issues of endogeneity with that one mediator. You're not dealing with the case of, well, I have like, you know, K much greater than N potential mediators that I measure in my data, and I'm trying to leverage the fact that I measure many, many different mediators to then actually to basically, so you could think of a machine learning algorithm where you leverage not just the fact that you have many X's, but also that you have many M's. And so there you might be sort of ruling out confounded stuff that would be sort of not by, you know, in your assumption, all of the confounding can be controlled for via X, but it doesn't allow for any potential other mediators that would be correlated. Is that right? So like you could think of a different algorithm, but this isn't that.
Yeah, so that's a very good comment you're making here, because the idea in this paper is really to have either only one or a fixed amount of predefined mediators. Okay. So you could also have several mediators in our framework, because what you see here, our estimation approach relies on this propensity score here. So the M here could contain several mediators, but the important thing is that you fix the mediators in advance which you are interested in. Mm-hmm. And they must be not high dimensional, so a small amount of mediators. So then this high dimensional setting here to control the X variables. Now, what you pointed out is a different way one could use mediation analysis. Namely, one could also use mediation analysis to find the important mediators among high dimensional mediators, among a large set of potential mediators. This is something we don't do in this paper, and I don't know what the asymptotic properties of this approach would be, but that's a very interesting, problem. I think there are already, someone has written a paper on this as well, how to select among high dimensional mediators. I cannot remember now, but that's not the problem we look at here. But also the other problem is of course interesting, because the other thing would tell you what are the important mechanisms, right? It would explore in the data which mechanisms are actually important. Here we say, okay, we are interested a priori in whether a specific mechanism exists.
I mean, presumably you can always just do some sort of machine learning type algorithm where you look at like try to find the mediators as by just regressing treatment on that outcome, but doing that in a flipped way. I think Sundal has a paper along those lines as well, right? So selecting.
But then you would, for each of these many mediators, you would still need to assume that you have all the access to counting for each of these.
So there you would find the set of potential mediators, because you would see which thing did the treatment have an impact on, but you would have the causal impact of those mediators. So you'd never get that. So you still need an algorithm or some sort of assumptions and an algorithm to second bit. Mm-hmm. I guess. Yeah. Okay. Sorry. Thank you very much for that.
Yeah. Thanks for the question. So let me, if there are no more questions, let me conclude the talk with a small empirical illustration of the method. So we apply the method to the National Longitudinal Survey of Youth, And this is a representative survey of roughly 9,000 individuals that were born in the years 80 until 84. And it's a US data set. And our treatment variable of interest here is health insurance coverage at the 2006 interview. And what we want to know is the short-term health effect of health insurance coverage on self-reported general health in the year 2008. And we are interested in whether this effect actually is mediated by routine checkups, which happened between 2006 and 2007. So this is to say, if we discover a short-term health insurance effect on general health, is this due to routine checkups because some deficiency has been found in a routine checkup? Or is it a direct effect, which is then maybe explained by acute symptoms, and then if you have such an emergency, you directly go to the doctor, right? And this is actually a context where we have a large set of controls, because the National Longitudinal Survey of Youth contains 770 control variables that we could use, and many of them are dummy variables. And what I also should say is that we also include dummies for missing values of the control variables. And these control variables are measured prior to our treatment year. And actually the range of control variables covers almost anything you could imagine in terms of socioeconomic characteristics. So previous health, for example, education, income, family status, even information on the parents and other family members, and so on and so forth. And then we just provide these 770 control variables. And here, this is just descriptive, showing that the treated and the non-treated are in fact not comparable in many of the important control variables. For example, among the treated, we have a higher share of females than among the non-treated. We also see differences in terms of who goes to a routine checkup and who doesn't. And then we estimate this direct and indirect effects by using either the Chetgen and Spitzer score function, or our modified score function using Bayes rule, where we don't depend on the density estimation. The estimator which we use several ones, but I think the results I have here are for the Lasso Estimator. So we pick the important covariates by means of Lasso. And what we generally find is that we have an effect in terms of the total effect. So the average treatment effect is negative. And here negative is good because the variable is coded such that 1 is excellent health and 5 is poor health. And now the question is, this total short-term health effect, does it operate through routine checkups or not? And here we generally find the indirect effect, no matter whether it's indirect effect under treatment or non-treatment. We generally find that with both methods to be close to 0, even though here in our methods it's statistically significant at the 10% level. But in general, the picture we get is that the indirect effect is actually not so important through routine checkups, whereas the direct effect is usually close to the total effect, and again not always significant, because estimating direct and indirect effects is actually a harder problem, and in terms of the results, you very often get larger standard errors than for estimating the total effect. But in general, you see in 3 out of 4 cases it's significant at the 10% level and very close to the direct effect. So we find at least we find some limited evidence that the short-term health effects of health coverage don't operate through routine checkups. But of course, these are only the short-term effects, right? In the long run, you would expect that routine checkups are important for finding chronic diseases, for example. Okay, so let me conclude. So we combine causal mediation analysis with double machine learning and show root inconsistency of the estimator. We also have a small simulation study and an application. Yeah, so thanks a lot. And if there are any questions, I'm happy to answer them.
Thank you very much, Martin. Questions, maybe Klaus, are you?
Yes, can you hear me?
Yeah.
Perfect.
Yeah, now I can hear you.
Okay. So on the estimation with the plugin estimators. So what you essentially need is that the score, which is predicted from those plugin estimators, represents a probability.
In our case, the score functions we use actually, so we average over them, and then it's actually an average. So it's not that the score is necessary. No, actually, in general, the score is not a probability.
Yes, exactly. So that's why. So usually machine learning, what you would do would be you would do empirical calibration to check or to make this score kind of like a probability. But another option would be, couldn't you just use, for example, variational Bayes framework and fit those estimators? Because then this would be a probability if that's needed.
And how would that exactly work? So I have to say, I'm unfortunately not familiar with the method you're pointing out. So, so what would you do it?
Oh, it's like an estimation method. It's a different way of estimating.
The plugin estimators?
Pardon? Yes.
The plugin estimators? Ah, okay.
Yes. For example, it works with, I don't know, with neural networks or whatever, yeah. Not so much.
Ah, okay.
So it's a way of like how you, the thing is with, if you estimate a neural network, you usually estimate the weights with gradient descent. And you follow this path of bias variance trade-off.
Yes,
but
exactly.
You can also force it to kind of train it in a probabilistic way, where you make sure that when you calculate the gradients, it's our true gradients. Yeah.
I see now. I see what you're pointing at. Yeah, that's a very good point. So then my question would actually be whether someone has shown that this approach you just mentioned also attains this n to the power of -1/4 rate, right? Because if one can show this approach as well, then you could also use this one as a plugin estimator here.
Yeah.
That would be the crucial question then.
Victoria?
Yes, thank you. So I actually just had a question on with regards to like how so for like the application or the simulation that you do and you show the sort of, you decompose the effects, and that was nice. I was wondering if you could show like what you would get if you had like a more naive estimation, that, you know, the way that you see people doing it in papers oftentimes, where you just put the mediator on the right hand side and you control for the right x's. Do you get the right result, or do you need to use the algorithm that you propose to actually get a more plausible result? So just sort of having a comparison of what would happen if you did it in the naive way, assuming you like landed on the right x's that you've wanting to control for.
I think we lost the speaker.
Oh.
Oh.
Oh no. Sorry. Too many questions.
No. Oh.
Your questions are too tough, Vicky.
Yeah,
Come on, you just ran away.
This time it's not even, I mean, you know, normally it's Australian internet we can blame. There's Martin.
Martin, we can't hear you.
Now we can hear you, Martin.
Yeah, sorry, I suddenly I was kicked out, but now I'm back.
Okay.
There are other questions.
Sorry, Vicky, you have to repeat your question.
Okay, sure thing. Yeah, so I was just wondering for the application and the simulation, whether you could sort of do a comparison with the naive a sort of mediation estimator that you see people doing, where they just basically control for the mediator on the right-hand side along with the treatment indicator, and you just put in, you know, sort of the right X's or close to the right X's or something like that, which would be so typical that you would find. I mean, does under the assumptions that you have, how close would you get it if you had the right X's, or, you know, how, I guess it would just be curious whether the estimator that you're using is how much more efficient it is, or not efficient, how much better is it than doing this naive approach?
Yeah, you cannot give a general answer to this question, because it really depends how well the naive approach works in terms of using the correct confounders, or whether you need to use confounders at all, right? So if a researcher knows exactly which are the important confounders, and the researcher's intuition is right about the confounders to be used, then this approach I'm mentioning does not have any, then our approach does not have any value added, right? So, however, if you're in a scenario where you're maybe not so sure what the correct confounders are, and your choice could be the wrong one, right? Then this method gives you the opportunity to do it in a data-driven way, right?
Yeah.
And in practice, actually, there are now quite a few papers that compare machine learners with classical treatment evaluation, where the researchers pick the X variables, and sometimes they find very similar results, and sometimes they find quite different results, right? So it depends on the application, and therefore it's at least a good way to check the researcher intuition, I would say. So I would say one can always do it on top on what one does anyway, right?
Yeah.
To see how robust things are.
Right. So, but conditional on knowing the X's, then the OLS strategy would work.
Yeah, then the standard strategy would work. I mean, the OLS strategy also depends on the linearity assumption, right?
Right, exactly.
But you can also use another non-parametric method to use them with the X, like inverse probability weighting or matching or whatever. And that would then work here, if you know all the X's.
Yep, great. Thank you.
Yeah.
I have a quick question. Hey, Martin.
Hey, Johannes, how's it going?
Good. Well, you know, sitting at home. So I just had a question. I think it's something you told me like a year ago, or that was a big discussion on the labor seminar, where if you fit a machine learning, you shouldn't interpret the X's, right? Because correct, it depends on the sample you have, and you shouldn't really, like, there's good arguments not to do this. So maybe just the intuition, why can we do this now here?
You mean why can we do this without interpreting the X variables, or?
Yeah, I mean here somehow your M is right. It's we want to interpret, is it employment, is it whatever? So that's somehow like just interpreting a covariate in machine learning, or why isn't it?
Concerning the X, it's still the same thing. We don't interpret the X's. So we don't interpret the effect of the X's on M or D or Y, because what we want to do is we just want to fit this function, the conditional mean, the propensity score as well as possible. And it could be that if two X's are strongly correlated, then just for predicting the propensity score or the conditional mean, it can be beneficial to drop one of the X's. And therefore, the conclusion must not be that the other X does not have a causal effect on M or D or Y, but it's simply for the machine learner for predicting the function which we need. Actually, it suffices to have one of the X's. That's the reason why we should not interpret the coefficients on the X's, right? But of course, we interpret the effects of M on Y, not directly, but they are part of the indirect effect, right? So here actually, what we actually try to do is we try to get rid of the influence of the X's in our system of variables to then be able to disentangle the direct and the indirect effect.
Right? So suppose I have, as you just said, you have two X's and you drop one because it's irrelevant for prediction. It's actually part of, you know, the real model or whatever, but it's just for prediction, it's not useful. would that change anything about the conclusions? Like, would I see another M potentially now being selected due to that?
Another M or another X?
No, another M, like another mediator. So, you know, you have a new, it selects a different set, right? The machine learner. And now could it happen that I make it wrong or a different judgment for a different M, for example? If I test two
Yes,
Ms.
of course. So the thing is, here the idea is we fix the M we're interested in a priori, right? We say explicitly, look, I want to do it for this mediator. Now, for a different mediator, you might need different control variables, right? Because it always depends on which variables jointly affect the M and the Y, for example, right? So the thing we do for one problem, for one specific M, is not necessarily the appropriate thing in terms of picking the X variables for a different mediator. Yeah.
So when I compare two different M's and, you know, do this, that's an issue, no? Then?
Well, you want to compare two different causal paths. Is that what you're saying?
Yeah.
What you can do, for example, in our framework is you can run two estimations, one where you only include one of the M's, and then where you include both, and then you would see what the contribution of the second one is, conditional on the first one, which was already in there, right? Because also M's can come out, right? So, yeah.
And just the last thing, if I reverse the order in just what you explained, would that give me the same answer?
If you reverse the order...
So if I test the other M first and then both, could it?
No, because as I said, right, if you have correlation between the M's, right, if the M are also correlated among them, then it's path dependent what you get, right? Because the indirect effect of one M is conditional on the other M being already in there or not, right? It's a similar problem as in weight decompositions, by the way. Characteristics do you include first, right? If you start, because weight decomposition is also something related to direct and indirect effects.
Cool. Thanks.
Okay, excellent. Are there any more questions? No, super. Thank you very much, Martin. It was a pleasure to have you here.
Thanks for inviting me again.
As usual with our speakers, all we can do at the moment is